Everyone has heard of Mercury, the first planet in the solar system, located so close to the sun that it seems to be bathed in brilliant light. But there is an interesting fact. Although it has been known since ancient times, this is the rocky planet least explored by humans. So why has a world right before our eyes been overlooked? Is it really boring, or is it hiding secrets that could change our understanding of the universe? In this video, we will decode the strange things about Mercury, from its characteristics and history to the space missions that have visited it. Stay tuned until the end and don't forget to subscribe to the channel so you won't miss the next exciting journeys beyond the universe. When it comes to Mercury, most of us tend to imagine it as just a tiny planet, closest to the sun, with nothing particularly interesting to explore. But the truth is the opposite. Mercury is a strange world, where every imagined step reveals a series of mysteries that challenge human curiosity. It is not merely a rock floating in space. It is a unique planet with a formation history, structure, and harsh environment that would astonish any scientist. The first thing to mention is Mercury's composition. Unlike the common perception that rocky planets are mostly made of silicates, Mercury resembles a gigantic metal block with a thin outer shell. Nearly 70% of the planet's mass is iron and nickel, while only about 30% consists of rocky material. This ratio makes Mercury the second densest planet in the solar system, just slightly less than Earth. However, if we assume both planets were the same size, their surface gravity would be nearly identical. This demonstrates that despite its small size, Mercury hides a colossal metal heart relative to its dimensions. From this composition, we begin to see a paradox. Mercury is much smaller than Earth, even smaller than some moons in the solar system, such as Ganymede or Titan, yet its mass is dominant. Ganymede, the largest moon of Jupiter, has a diameter larger than Mercury, but since it is mainly composed of ice and light rock, its mass is less than half. This indicates that Mercury formed under special conditions, possibly involving massive collisions in its early history that stripped away much of the silicate-rich outer layer, leaving the concentrated metal core we see today. Moving to the surface, Mercury resembles our moon with countless impact craters and lava plains. However, upon closer observation, you will notice unique features. One of the most striking phenomena is the existence of scarps, curved mountain ranges stretching hundreds of kilometers. They were formed when Mercury's core cooled and contracted, causing the entire solid crust of the planet to wrinkle like a shriveled apple. This suggests that the planet once experienced strong geological activity, although today it is nearly dead in terms of internal energy. The Caloris Basin cannot be overlooked, a massive scar on Mercury's surface. With a diameter of over 1,500 kilometers, it is one of the largest impact craters in the solar system. The collision that formed this basin was so powerful that it not only carved deep into the surface, but also created cracks, widespread lava flows, and deformed terrain on the opposite side of the planet, what we now call the chaotic terrain. Imagine an explosion so intense that it shakes the entire planet from end to end. That is exactly what happened on Mercury billions of years ago. If the surface tells a story of violent impacts, Mercury's temperature reveals another aspect: extreme harshness. Being so close to the sun, the planet experiences the most extreme temperature fluctuations among rocky planets. During the day, under direct sunlight, the surface temperature can exceed 400 degrees Celsius, enough to melt lead. But when night falls, the almost non-existent atmosphere cannot retain heat, and temperatures plunge below minus 170 degrees Celsius. This enormous difference transforms Mercury into a world where blazing heat and freezing cold alternate within just a few Earth days. Even more fascinating, at Mercury's poles exist deep craters permanently shrouded in darkness, where temperatures never exceed 990 degrees Celsius. And it is here that scientists have discovered the presence of water ice. It is hard to believe that a planet so close to the sun can preserve ice within itself. This not only raises questions about the origin of this water, possibly delivered by comets or asteroids, but also opens up possibilities for hidden scientific treasures within. Beyond surface mysteries, Mercury also has another unexpected feature: a magnetic field. Although only about 1% the strength of Earth's magnetic field, it is still strong enough to partially shield against the harsh solar wind. This astonishes scientists even more, as Mercury's small size should have caused its iron core to cool long ago. The existence of this magnetic field suggests that the interior core is still somewhat active, and understanding it could help us decode more about the evolution of magnetic fields in other rocky planets, including Earth. Another noteworthy detail is Mercury's strange orbit and rotation. Rather than being tidally locked to the Sun as once thought, the planet follows a rare resonance rule. For every 3 rotations on its axis, Mercury completes 2 revolutions around the Sun. This creates strangely long solar days. From one sunrise to the next on Mercury, you would have to wait 2 Mercury years, or about 176 Earth days. Standing on the surface, you would witness a unique sight. The sun rises, slows down, reverses direction, then continues to set. A complex and enchanting solar cycle that is almost unbelievable when just heard about. All of the above factors, metallic composition, high density, scarred surface, extreme temperatures, traces of water ice, and unexpected magnetic field, make Mercury a planet that is both familiar and alien. It may look like the moon in appearance, but it possesses unique characteristics that deserve much deeper study. And these very features make this tiny planet one of the greatest challenges in humanity's quest to explore space. Exploring Mercury has never been a simple journey. If landing on the moon was a great milestone for humanity, then putting a spacecraft into orbit around the planet closest to the sun is a technical challenge no less dramatic. The reason is simple. The sun's immense gravitational pull turns every attempt to approach Mercury into a life or death struggle with gravity. A spacecraft must not only be sturdy enough to withstand temperatures capable of melting metal, but also carry enough fuel to slow down. Otherwise, it will either be flung into space or crash straight into the giant star. Because of this, after the initial success of Mariner 10 in the 1970s, the space science community had almost to leave Mercury untouched for more than 3 decades. At that time, engineers could not find a solution to balance the massive fuel requirements with the limited space for scientific instruments. Adding more fuel meant reducing research tools, and conversely, carrying enough instruments left the spacecraft with no way to slow down enough to enter orbit. Then, a revolutionary idea emerged. In the mid-1980s, orbital mechanics expert Trần Vạn Yin pointed out that instead of directly fighting the sun, why not use other planets to borrow force, to decelerate? Like a figure skater spinning around an opponent to change direction, a spacecraft could fly past planets, using their gravitational pull to adjust its velocity. This idea was not only theoretically feasible, but also outlined a specific trajectory, orbiting Earth, making multiple flybys of Venus, and approaching Mercury step by step instead of rushing straight in. NASA applied this exact plan with the Messenger mission, launched in 2004. The tiny probe, weighing only about 1 ton, contained advanced technology and a special ceramic heat shield to withstand sunlight 7 times stronger than on Earth. Messenger undertook a nearly 7-year journey around the solar system, flying past Earth, Venus, and then making multiple close flybys of Mercury before finally entering orbit in 2011. During this time, Messenger repeatedly tested the nerves of the ground control team. On one occasion, it entered safe mode while flying past Mercury, causing everyone to worry that the entire mission might fail just a few steps from the finish line. Fortunately, the automated system restarted in time and the spacecraft continued its journey. Upon entering Mercury's orbit, Messenger became the first spacecraft in history to orbit this planet. A spectacular victory for both science and engineering. What made Messenger special was not only its arduous journey, but also the volume of data it sent back. Before Messenger, we had mapped less than half of Mercury's surface. But during its 4 years of operation, the spacecraft captured over 200,000 images, allowing humanity to see the entire planet at unprecedented resolution. Color images revealed that Mercury's surface is not merely a monotonous gray, as once thought, but contains subtle color variations, reflecting differences in minerals and geological history. One of the most surprising discoveries was the presence of water ice at Mercury's poles. In permanently shadowed deep craters, radar from Messenger confirmed the presence of reflective ice deposits. This means that even on a planet only tens of millions of kilometers from the sun, where daytime temperatures can melt metal, there exist frozen oases hidden deep within eternal darkness. The immediate question arises: where did this ice come from? It may have been delivered by comets and ice rich meteoroids in the past, or perhaps from water vapor escaping from Mercury itself. Regardless of its origin, this discovery opened a completely new avenue of research into the possibility of water existing in the harshest environments. Messenger also revealed many secrets about Mercury's weak yet unexpected magnetic field. Though only 1% the strength of Earth's, it is still strong enough to interact with the solar wind, creating a dynamic and chaotic magnetosphere. Measurements showed that magnetic reconnection events, when magnetic field lines are broken and reformed, occur around Mercury hundreds of times more frequently than on Earth. Each event releases enormous energy, producing high energy electron bursts. These observations not only help us better understand the tiny planet, but also offer lessons about how magnetic fields protect a planet's atmosphere and surface from cosmic radiation. Additionally, using spectroscopic instruments, Messenger provided convincing evidence that Mercury's surface contains high sulfur content, a surprising discovery, as it was previously thought that the planet was too close to the sun to retain such a volatile element. The presence of sulfur and other elements indicates that Mercury's formation history is far more complex than expected, forcing scientists to revise models of rocky planet evolution. But every journey has an end. After more than a decade of operation, in 2015, Messenger ran out of fuel. NASA decided to let the spacecraft end its life by crashing it onto Mercury's surface, creating a small impact crater, a permanent mark that humanity had once been there. Before disappearing, Messenger managed to send back a treasure trove of data, completely transforming our understanding of Mercury from a forgotten planet into one of the most fascinating and mysterious worlds. Messenger's success also proves one thing: in the universe, no limit is absolute. Challenges that seem insurmountable, like sending a tiny spacecraft to withstand intense heat and the sun's tremendous gravitational pull, can be overcome with human imagination, creativity, and perseverance. And it is this spirit that has transformed Mercury from a faint speck in the sky into a world full of stories, gradually revealing secrets about the history of the entire solar system. Mercury, with its barren surface and extreme temperatures, is not just a simple rocky planet. Messenger showed us that, despite its fragility, the planet's outer layer, its extremely thin atmosphere, contains vibrant mysteries. This is not an atmosphere thick enough to interact strongly with particles, but an environment where each atom and ion moves almost independently. Yet this allows Messenger to measure each particle individually. The probe's spectrometer detected sodium, potassium, magnesium, calcium, and even chlorine, volatile elements previously thought to exist only on cold or mineral-rich planets. Interestingly, Mercury's surface does not retain these elements. They are destroyed by solar radiation around the equator and rise into the outer layer. As a result, particles like potassium and sodium are more concentrated in the northern hemisphere, where temperatures are cooler. Remarkably, this outer layer is unstable. Solar wind and radiation pressure continuously sweep away neutral and charged particles from the planet. But the outer layer does not only receive elements from the surface. Messenger also detected hydrogen and helium, which do not exist on the surface, being supplied directly by the solar wind. These discoveries clarify a mechanism maintaining a delicate dynamic balance, making Mercury an extremely active planet despite its small size. Another strange phenomenon is the presence of calcium and magnesium in the outer layer, appearing at different times of the day. Calcium is prominent at sunrise, while magnesium appears mostly from the dark side. This outer layer also creates a comet-like tail, as sodium ions glow when blown away from the planet. From a distance, Mercury may look like a pale yellow star with a long streak, changing according to the planet's eccentric orbit. And notably, water, an element seemingly impossible to exist on a planet so close to the sun, has significant traces at both poles, deep within permanently shadowed craters. The estimated ice amounts to trillions of kilograms, enough to become a potential water source for future colonies. But Mercury is not only young in its outer layer, Its surface tells a story of high past temperatures and intense volcanic activity. Impact craters such as Raditladi or Rastelli reveal traces of ancient lava, smooth inside, while the edges remain rugged. Messenger showed that lava not only filled the craters created by meteor impacts, but also flowed from highlands into basins, forming vast, dark orange valleys. This process is similar to freely flowing water. Molten lava seeks the lowest ground, then cools and solidifies, leaving clear traces of past volcanic activity. Mercury's lava flows also reveal details about the extreme temperatures the planet once experienced. Although the current surface reaches about 430 degrees Celsius during the day, molten rock layers must have reached 600 to 300 degrees Celsius to become magma. The viscosity of Mercury's lava is estimated to be thousands of times that of water, like slowly flowing ketchup, allowing it to spread tens of kilometers before cooling. These ancient lava flows help explain why many impact craters have smooth floors but rugged rims. Lava filled in surface irregularities, creating an insulating layer, allowing the magma inside to flow freely until it completely cooled. One of the most intriguing discoveries is the planet's contraction. Messenger measured that Mercury has shrunk over 14 kilometers in diameter since its formation. Cracks and grooves on the surface indicate that the crust once expanded and is now contracting, a phenomenon related to core cooling. This not only explains the long fissures on the surface, but also shows that the planet is still evolving geologically, albeit much, much more slowly than during its intense volcanic period. Messenger also revealed a fine layer of dust covering ancient lava regions. Scientists recognize this dust as volcanic ash, ejected from vents and settling on the surrounding terrain, like hot snow covering Mercury. The combination of ancient lava, volcanic ash, and particles in the outer layer creates a complex picture of this small but highly dynamic planet. Each crater, lava flow, and particle in the outer layer tells a story of Mercury's chaotic past and delicately balanced present. From charged particles in the outer layer to permanent ice at the poles, from magma flowing through craters to contraction grooves from a cooling crust, Messenger helped us understand that even a seemingly barren and scorching planet holds profound mysteries, intricate balancing mechanisms, and a rich geological history. More importantly, these discoveries open up many new avenues of research. They raise questions about the origin of volatile elements, how ancient magma moved on a planet close to the sun, and the interaction between solar wind and the outer layer. These questions are not only relevant to Mercury, but also help us better understand rocky planets in general, from Earth to distant worlds in the universe. Messenger demonstrated that, despite its small size, Mercury remains a natural laboratory for planetary physics, chemistry, and geology, and each discovery challenges our previous understanding. Messenger has concluded its physical journey, but its scientific legacy remains vivid. It transformed Mercury from a faint speck in the sky into a planet rich in data, color, and geological history, revealing untold stories of a place where the sun nearly scorches everything around it. And each photo, each measurement from Messenger is a reminder that, in the universe, even the seemingly most barren planets hold mysteries waiting to be explored. Mercury is not just a barren planet, but also a vibrant stage for extreme geological phenomena. When observing volcanoes such as Navoy, it becomes clear that this planet once experienced terrifying geological fury. This crater, with a diameter of 66 kilometers, was not formed by a typical meteorite impact. Scientists determined that the eruptive force from within was strong enough to scatter massive rocks and debris around, creating a central peak unlike any standard impact crater. The principle behind the formation of this central peak is quite interesting. When loose material such as rocks or sand is thrown into a new crater, it slides down the crater walls and collides at the center. All this energy forces the material to continue moving upward, forming a raised peak. The shape of the central peak also depends on the angle of impact and the force, but Navoy's central peak is completely different, demonstrating the raw power of once active volcanoes on Mercury. These eruptions not only expelled lava and debris, but also created showers of scorching ash, turning the sky and surface into a chaotic scene. But it is not just volcanoes. Mercury's surface also records many other stories through craters and ray systems. Craters with sharp rims indicate young impacts, while older craters with eroded rims show that the surface has undergone billions of years of change. Some craters overlap, creating complex geological layers, revealing the planet's violent collision history. Notably, the prominent ray systems on the surface, thin streaks extending hundreds of kilometers, testify to catastrophic impacts where material from beneath the surface was ejected, forming intricate patterns previously unexplained by scientists. Another fascinating discovery involves the Apollodorus crater and the surrounding Pantheon pits. Radial cracks resemble shattered glass, reflecting the brittle and hard nature of the crust at the time of eruption. Unlike typical round impact craters, these cracks indicate that subsurface magma experienced extreme pressure, spreading along radial paths and forming unique grooves. This is evidence that Mercury's surface was deformed not only by external impacts, but also by internal pressure from within the planet. Ancient lava flows provide further evidence that Mercury was once a melting planet. Lava from eruptions filled craters, creating smooth surfaces while preserving the rugged terrain around them. These flows not only filled impact craters, but also ran into valleys, flowing into basins and transforming highlands into the dark orange surfaces we see today. This spread indicates that the lava was highly viscous, able to travel tens of kilometers before cooling, yet soft enough to fill surface irregularities. In particular, scars and grooves on the surface show that Mercury is still cooling and contracting. Some long strips of land appeared as the crust shrank, while craters and surrounding areas indicate that subsidence occurred unevenly. Part of a crater retained its shape, while another part slipped down, revealing that soil and rock have different hardness or were affected by impact forces unevenly. These irregularities remain open questions, emphasizing that Mercury is a challenging and mysterious planet. Surface colors also tell a story. Dark patches indicate high graphite content, while brighter regions, such as ray systems, contain different chemical components less affected by solar radiation. Scientists discovered that these rays, extending hundreds of kilometers, are actually formed by how material interacts with rugged terrain rather than entirely depending on impact force or chemical composition. A notable example is an experiment by a group of students under Tapan Sabuala's supervision who created a rough test surface and reproduced the spiderweb-like patterns of the ray systems, which prior standardized laboratories could not achieve. This shows that Mercury's natural terrain plays a crucial role in how impact energy spreads and forms unique structures. The massive ray system from the Hokusai crater is clear evidence of intense impacts. Its rays almost cover the entire surface of Mercury, with a perimeter of up to 15,000 kilometers. Smaller ray systems like Ducey also extend over 1,000 kilometers. Compared to the Moon, where rays are usually small and narrow, these gigantic systems are a visual hallmark of Mercury, reflecting how the sun's strong gravity affects impacting objects, propelling them to create massive rays. Another factor making Mercury research difficult is its weak gravity, which prevents the planet from holding onto objects as long as Earth's moons do. Therefore, all geological traces we observe result from extreme processes, both external forces and the planet's internal forces. Every crack, ray system, and lava flow is vivid evidence of the planet's violent and dynamic history. Messenger Mariner 10 and the Bepi Colombo mission are keys to understanding these mysteries. Messenger is particularly important as the only mission that placed us into orbit around Mercury, providing unprecedented close-up images. Thanks to this, we can identify giant ray systems, ancient lava flows, complex impact craters, and unique geological features, constructing a detailed picture of the planet's violent yet wondrous past. Mercury, though now calm under the sun's scorching light, still retains all traces of its chaotic past. From fierce eruptions, overflowing lava flows, spiderweb-like ray systems, to radial cracks resembling shattered glass, all of this creates a vivid story of a planet that was melting, but has learned to remain tranquil. Venus, outwardly appearing as a beautiful and peaceful planet, is in reality a world full of harshness and mystery. Viewed from space, its thick clouds of pale yellow and ivory give the planet an elegant, gentle appearance, causing anyone seeing it for the first time to mistakenly perceive tranquility. But just peel away this cloud cover, and underneath lies a true hell, an average surface temperature of 462 degrees Celsius, an atmospheric pressure 92 times that of Earth, and sulfuric acid rain that never reaches the ground, evaporating in the dense CO2 layer, yet still enough to make the planet an environment in which any human could survive for only a few seconds. What makes Venus particularly fascinating to scientists is its simultaneous similarity and difference to Earth. The planet's diameter is only 640 kilometers smaller than Earth's, with nearly identical mass and density, sometimes earning it the nickname sister planet, or twin of ours. However, while Earth has a relatively temperate environment, Venus embodies the raw power of climate and geology, a rocky planet that is anything but gentle. All these factors highlight Venus's critical role in studying the evolution of rocky planets in the solar system. One of the most intriguing features is the planet's retrograde rotation. Unlike most other planets rotating counterclockwise on their axes, Venus rotates clockwise, with a full rotation taking 243 Earth days. This results in solar days longer than a Venusian year, but due to rotating opposite to its orbit around the Sun, a solar day from one sunrise to the next lasts only 117 Earth days, less than half of an actual planetary rotation. The slow rotation at the equator, only 6.5 kilometers per hour, makes Venus the slowest rotating planet in the solar system and renders its atmospheric and energy circulation mechanisms completely different from Earth's. Venus's atmosphere is one of its most distinctive features. Composed mainly of CO2 with dense clouds of sulfur dioxide, it creates an extreme greenhouse effect, trapping solar heat like a gigantic thermos. Surface temperatures on Venus are even higher than Mercury's, despite Mercury receiving more solar radiation. This is because Mercury, though closer to the Sun, lacks an atmosphere, whereas Venus's dense atmosphere retains heat steadily day and night. Even at the poles, temperatures fluctuate very little, while the immense atmospheric pressure exerts a compressive force on all surface objects, equivalent to the pressure beneath 1 kilometer of water on Earth. Venus also stands out for its winds and atmospheric dynamics. While surface winds reach only a few kilometers per hour, the dense atmosphere allows them to move small rocks and fine dust. In the cloud layers, wind speeds reach up to 300 kilometers per hour, causing clouds to circle the planet in just 4 to 5 Earth days, making the planet appear to rotate much faster than it actually does. These winds, combined with the thick sulfuric acid clouds, create highly dynamic and complex patterns, making surface observation from space extremely difficult. The surface of Venus tells a story of intense geology. Scientists have discovered numerous ancient volcanoes and massive lava flows, indicating that the planet experienced multiple violent eruptions. Some volcano craters on Venus are hundreds of kilometers in diameter, with complex structures sometimes containing grooves and central peaks similar to those on Mercury. But under the effects of extreme pressure and temperature, erupted material has deformed uniquely. This provides evidence of the latent geological power and geological evolution processes that we do not yet fully understand. Not only volcanoes, but ancient impact craters also recount Venus's violent history. Some crater rims are deformed, subsided, or even cracked like glass, prompting questions about their origin. It is possible that this resulted from pressure from below, where hot magma suddenly pushed upward rather than external meteorite impacts. This suggests that Venus may have experienced extremely strong internal quakes, causing the crust to crack without leaving direct impact traces. These discoveries are not only evidence of harshness, but also raise questions about how the planet evolved. Similar to Mercury, where massive ray systems and complex craters reveal a violent past, Venus is a planet where every geological phenomenon is amplified by its harsh environment: high pressure, extreme temperatures, dense atmosphere, and corrosive clouds. Each groove, volcano, and impact crater is a valuable geological record waiting for scientists to decode. Modern missions like Bepi Colombo will help us better understand Venus's magnetosphere, exosphere, and geology. These data will supplement the overall picture, helping explain unusual crustal fractures, ancient lava flows, and how the atmosphere interacts with the surface. Although no one has ever set foot on this planet through space missions, we have been observing a hellish planet existing alongside Earth, similar in size and mass, yet completely different in environment and latent power. While Venus always shines in the Earth's sky with an alluring appearance, that light is a veneer hiding a world of turbulence and danger. It is living evidence of the tremendous forces that can arise on a rocky planet. From the powerful effects of volcanoes and lava flows to the enormous pressure of the atmosphere and scorching temperatures, all combine to create a planet both familiar and alien, both beautiful and deadly. Venus, with all these contrasts, is one of the most fascinating planets in the solar system. It offers endless opportunities to learn how rocky planets form, evolve, and interact with harsh environments. Every crack, crater, and swirling cloud is a story of nature's primal power, waiting for us to decode. And it is precisely this contrast between captivating beauty and lethal harshness that makes Venus a unique planet worthy of study, admiration, and respect. From space, Venus appears as a brilliant golden gem, standing out against the darkness of the universe, shining as brightly as a daytime star or the early morning sun. But that dazzling light is only the surface of a world full of challenges, where every step comes at the cost of extreme temperature and pressure. Beneath the thick cloud layer, the planet's atmosphere is a chemical labyrinth, dominated by CO2 mixed with sulfuric acid clouds, making any Earth like life impossible. Yet it is this very atmosphere that contains regions with conditions nearly Earth like, particularly at altitudes of about 50 to 60 kilometers above the surface. Here, pressure and temperature are relatively moderate, close to Earth's, and gravity is similar as well. With a sealed cabin or appropriate pressurization equipment, humans could survive. This is a rare corner of Venus where science fiction seems to become a tangible possibility. Looking down at the surface, the history of Venus exploration began in the 1960s, during the Cold War, when the Soviet Union and NASA raced to send probes. The Soviet Union pioneered with the Venera missions, among which Venera 7 in 1970 marked a significant milestone, the first spacecraft to land successfully on another planet and transmit data back to Earth. Although it survived just long enough to send basic data, surface temperatures reaching 475 degrees Celsius, this mission opened the first door for humans to approach a world almost entirely different from Earth. Subsequent probes, such as Venera 8, 9, 10, 13, and 14, returned numerous color images and critical data, providing deep insight into the terrain, from expansive lava plains to large impact craters and massive volcanoes. Venus's surface is primarily composed of cooled lava plains, covering about 80% of the planet. This is the result of an ancient crust with no plate tectonics like Earth, estimated to be 300 to 600 million years old. Ancient lava flows stretch across, sometimes covering hundreds of thousands of kilometers squares, and over 167 volcanoes have diameters exceeding 100 kilometers, reminiscent of the Hawaiian Islands on Earth, but on a much larger scale and density. Moreover, the impact craters are unique. All have diameters of 3 kilometers or more, as smaller meteorites burn up or fragment before reaching the surface due to the dense atmosphere. These craters and volcanoes not only testify to the planet's violent and thermal history, but also reveal unusual surface renewal mechanisms, where hot mantle material occasionally erupts, flows through the ancient crust, and reshapes the planet's appearance in unpredictable ways. Another aspect that makes Venus remarkable is the lack of a strong magnetic field. This is surprising, given that the planet's composition is almost identical to Earth's, from size to density. Studies suggest the reason may be that Venus has never experienced a major collision strong enough to kickstart a dynamo, as Earth did with the moon-forming impact. The absence of a magnetic field allows solar radiation and solar wind to strongly affect the atmosphere, sweeping away light molecules and forming a comet-like tail, although it is invisible to the naked eye. Yet this atmospheric tail demonstrates how the planet protects and interacts with the harsh space environment, albeit in a completely different way from Earth. The extreme conditions do not stop there. Average surface temperatures of 462 degrees Celsius, atmospheric pressure 92 times that of Earth, cloud top winds reaching 300 kilometers per hour, combined with sulfuric acid rain and ultraviolet radiation from the sun, create an unimaginable climate hell. The clouds reflect 34% of sunlight, helping explain why Venus always shines brightly in the Earth's sky, becoming the second brightest object after the moon. Beneath this yellowish cloud layer, everything is obscured, and probes must use radar or infrared wavelengths to penetrate and map the surface. This is why technologies like Venera, Venus Express, Magellan, and modern missions are so crucial. They not only provide images, but also measure chemical composition, surface structure, and physical properties, helping humans gain a comprehensive understanding of this planet. Another interesting feature is the atmospheric vortices on Venus, especially water like whirlpools at about 59 kilometers altitude, just above the cloud layer. They not only create unique climate phenomena, but also suggest regions that could be safe for temporary survival, with pressure, temperature, and gravity similar to Earth's. Here, with a sealed cabin or a suitable exploration vessel, humans could almost breathe and operate under relatively normal conditions, something seemingly impossible at the surface. These findings are not only scientifically significant, but also open prospects for future planetary travel and research in compatible atmospheric environments. Finally, what makes Venus special is not just the numbers, data, or images. It is the perfect contrast between beauty and danger. Dazzling light outside, but extreme pressure and temperature inside. Ancient volcanoes and vast lava plains on the surface, yet relatively mild conditions in the upper atmosphere. A planet similar in size and composition to Earth, yet lacking a magnetic field and directly exposed to cosmic radiation. All these combine to create a planet both familiar and alien, making Venus one of the most compelling celestial bodies to study and admire in the solar system. Human exploration, from Venera 7 to modern missions, is a testament to the relentless pursuit of knowledge and the desire to push boundaries. Every photo, every data set, every discovery is a piece of the overall picture of Venus, helping us not only understand this planet, but also reflect on Earth in a new light. A dynamic, stable planet that has also experienced billions of years of extreme upheaval, as Venus continues to demonstrate. While Venus's yellowish clouds conceal many secrets, advanced technologies are gradually lifting that veil, allowing humans to witness the complexity, power, and primordial beauty of our nearest sister planet.